Let us make Spanner's promise concrete. Imagine a bank with account A holding 12,000 rupees and account B holding 3,000. The bank stores them in Google Spanner, a SQL database spread across multiple locations. We will call this transfer T1. The Mumbai application submits T1 to Spanner, move 5,000 from A to B. Do the arithmetic with me. A must fall to 7,000 and B must rise to 8,000. Anything else means money disappeared or appeared. Only after Spanner has durably committed T1 and made its timestamp safe does it reply success to the Mumbai application. From the customer's point of view, T1 is now finished. That word finished is important. Only after Mumbai sees success, Frankfurt starts T2. T2 is read only, so it changes nothing. It is also a strong read, meaning it must include every transaction that completed before this read began. So, can Frankfurt still return the old balances? No. T1 visibly finished first. T2 must return A at 7,000 and B at 8,000. The rest of this video builds that guarantee one problem at a time. First, where do these rows live? A primary key is the value Spanner uses to order and locate a row. Here the keys are account/017 and account/018. Spanner cuts that ordered key space into movable ranges called splits. Because these two keys are next to each other, both begin in split 1. One copy would be a dangerous single point of failure, so Spanner stores copies of the split in locations designed not to fail together. Each copy is a replica. A replica can preserve data if another machine or location fails, but a new write needs agreement from a majority of the voting replicas. That majority is called a quorum. Who receives the write first? Each split elects its own leader. The leader orders writes for that split and sends them to its replicas. Mumbai leads split 1 in our example, but another split can have a different leader. There is no single leader for the whole database. Right now, A and B share one split, so one leader can coordinate T1. Later, we will move B to split 2. Then two leaders must still produce one atomic result. Atomic simply means both balance changes happen or neither does. Agreement inside one split and agreement across several splits are different problems. Split 1 has 3 voting replicas: Replica 1, Replica 2, and Replica 3. Replica 1 currently holds the leader role. It is not a fourth member. Before any vote is counted, R1 creates the proposal locally and sends the same T1 proposal to R2 and R3. Slot 42 is one numbered position in this split's ordered log. Network delivery can be uneven. R2 has the request while R3's copy is still in flight. Those are delivery states, not competing decisions. 0 votes have been counted, so no value is chosen yet. Paxos is the protocol that turns the separate deliveries into one durable decision. Now name the exact protocol step. Because a leader term is already established, Multi-Paxos goes directly to the accept step for this new log slot. A leader term is the number generation that identifies the current leader. The accept request says, durably record T1's complete mutation in slot 42. A becomes 7,000 and B becomes 8,000. R1 records it locally and sends the identical request to R2 and R3. Receiving the request is not yet a yes vote. A replica first records slot 42 durably. Only then does it return an accepted yes. Now count the answers. R1 has a local accepted yes. R2 returns an accepted yes to R1. R3 does not answer. 2 accepted votes out of 3 form the right quorum. So slot 42 is chosen and recoverable. Pause there. Chosen does not mean Mumbai has received success. Client success remains gated by commit wait, which may overlap replication. There are two ways a response may not count. A rejection is an explicit reply saying, I already follow a newer leader term. No response means the replica could not be reached. Here, R3 did not answer, it did not vote for a competing value. Either way, R1 and R2 already form the quorum. With only one yes, the right would not be chosen. Now let R1 fail after that quorum chose T1. A replacement leader queries the live quorum R2 and R3 before proposing anything new. R2 reports accepted slot 42. This works because every possible 2 of 3 quorum overlaps the quorum that chose the value. The replacement must therefore preserve T1. It cannot replace slot 42 with a different mutation. After recovering the chosen log entry, the replica can apply the mutation to materialized account state. That is Paxos's job here. One ordered, durable log per split. If a majority is unavailable, the split stops new writes instead of risking two histories. Paxos does not solve every other problem. TrueTime supplies real-time evidence. Commit wait gates the safe response, and two-phase commit makes one atomic decision across splits. Paxos answered which write survives a failure. It did not answer when one transaction must appear before another. Here is the edge case. Mumbai sees T1 succeed, and only afterward does Frankfurt start T2. That is the order the users observed. Why not compare the two server clocks? Because clocks drift. Mumbai's fast clock reads 10 o'clock and 3 milliseconds. Frankfurt's slow clock later reads 9:59 and 59.997 seconds. The event that really happened later now looks earlier. If Spanner treated either local reading as exact, it could reverse the order the applications actually observed. TrueTime avoids pretending that a clock reading is perfect. Its now API returns an interval, an earliest possible time and a latest possible time. In this example, real time is guaranteed to be somewhere from 96 through 104 milliseconds. The midpoint is 100. Epsilon is the uncertainty on either side, 4 milliseconds here, so the full interval is 8 milliseconds, or 2 epsilon. Spanner chooses commit timestamp S at the safe right edge, 104. But S may still be slightly ahead of real time, so success cannot be visible yet. On the next true time call, earliest is only 98. Since 98 has not passed S, the response gate stays closed. This deliberate pause is commit wait. Later, TrueTime returns 105 through 113. Now, even the earliest possible real time is greater than S. Spanner can safely reveal success. Better clock evidence creates a smaller epsilon and usually a shorter residual wait. Weaker evidence creates a wider interval and potentially a longer wait. Without a trustworthy bound, Spanner refuses to guess. TrueTime gives bounded time evidence, and commit wait converts that evidence into a real order guarantee. Paxos still handles replica agreement. Two-phase commit will handle one decision across splits. Now let us follow the actual write without skipping state. A starts at 12,000, B at 3,000, and T1 moves 5,000 from A to B. The request goes to the leader of split 1 because that split owns both rows. The leader reads A and B under compatible reader shared logs and checks that A has enough money. Before committing, it upgrades to write logs and computes pending values, A at 7,000 and B at 8,000. Pending means calculated but not yet visible as committed data. Next, spanner chooses commit timestamp s equal to 104 at the latest edge of the true time interval. The locks, pending mutation, and timestamp stay together, while R1, the split one leader, records the log entry locally and sends it to R2 and R3. When R2 also stores it, R1 and R2 form the 2 of 3 quorum. The transaction is internally committed and recoverable. The client still has no success, and some replicas may not have applied the mutation yet. At the same time, commit wait checks true time. Its next interval is 98 through 106. Earliest is still below S, so spanner keeps the response hidden. Replication and commit wait overlap after S is chosen. When true time's earliest bound reaches 105, it has finally passed S. Now, after both quorum durability and the time gate are satisfied, the leader can return success. In parallel, it applies the mutation and then releases its logs. The other replicas apply it too. Any read whose timestamp requires T1 waits until the mutation has been applied. At the settled state, Mumbai has success and every required reader can see A at 7,000 and B at 8,000. Paxos made the write recoverable, locking protected the pending state, commit wait made the timestamp safe. We need two internal windows, not just before and after client success. First, pause before the Paxos quorum commits T1. If strong read-only T2 starts here, T1 was not committed at T2's start. T2 may be ordered before T1 and return the complete old pair, or it may wait and return the complete new pair. Now cross the internal commit point but keep T1's success response hidden during commit wait. A strong read starting in the second window must include T1 because T1 was already committed before the read began. The read may wait until its timestamp is safe and the mutation is applied, but returning the old pair is no longer legal. In either window, it can never expose pending values or mix old A with new B. Now rewind to before either writer has changed the rows. Suppose T1 and a second read-write transaction, T3, both read the old balances. In Spanner's default serializable mode, those reads take shared locks and shared locks can coexist. The conflict appears when both transactions try to upgrade those locks and write the same rows. They cannot both commit from the old input. One proceeds while the other waits, or Spanner aborts one attempt. An aborted attempt changes no data. The client library retries its transaction body, rereads the current balances, and recomputes the update. That prevents a lost update calculated from stale input. Finally, move T2 past the client response boundary. If T2 starts after Mumbai observes T1's success, external consistency independently forces T1 before T2. The result is again A at 7,000 and B at 8,000. This after success rule is stronger because every observer can use the visible response as the ordering boundary. Let us prove the promise with illustrative timestamps. Start with the amber box. This first true time call belongs to T1's commit timestamp selection. It returns the uncertainty interval 96 through 104. That shaded interval is a clock uncertainty bound, not the duration of T1. Spanner chooses the upper bound, so S equals 104. Now look at the separate green box. This is a later true time call made during commit wait. Its earliest bound is 105. Because 105 is strictly greater than S, real time must already be past T1's commit timestamp, and the response gate can open. Only after that gate opens does the Mumbai application observe success. From here, the horizontal placement shows order, not extra assigned timestamp values. Gate opens, success is observed, and then T2 starts. The observed success creates the real user visible boundary we care about. Frankfurt starts strong red T2 after that boundary, not while T1 is still finishing. That ordering forces T2's real timestamp to be greater than 104. Since T1 committed at 104, T2's snapshot must include T1's complete versions, A at 7000 and B at 8000. Now we can name the guarantee. Serializable means the transactions fit one valid sequence. External consistency adds the real-time rule. If users observe T1 finish before T2 begins, spanner cannot serialize T2 before T1. Now let us test a different overlap. A long report opens with read timestamp 100 when A is 12,000 and B is 3,000. The violet bar means the report remains pinned to snapshot 100 while the report stays open. It does not move through later timestamps. T1 then commits the transfer at version timestamp 112, producing A at 7,000 and B at 8,000. The green bar means those versions exist from timestamp 112 onward. It is not the duration of the transfer. Why keep both states? If the database stored only the latest value, it would have two bad choices. Block T1 until the report ends, or let the report read A from snapshot 100 and B from version 112. That mixed pair does not correspond to any legal single timestamp snapshot. Spanner avoids both choices with multi-version concurrency control, or MVCC. Instead of immediately destroying the previous value, each row keeps immutable committed versions tagged with their commit timestamps. A and B have separate version histories. The database does not store the account pair as one object. At timestamp 90, the earlier illustrative versions are A at 10,000 and B at 5,000. By timestamp 100, before T1, they are A at 12,000 and B at 3,000. The shared read timestamp is what reconstructs one consistent database snapshot. Here, snapshot means the committed database state as of one chosen timestamp. Because this report is pinned to 100, Spanner applies the same rule to every row. Choose the newest committed version whose timestamp is less than or equal to 100. That selects A at 12,000 and B at 3,000. The versions at 112 are too new for this report, even though T1 may commit while the report is still running. A later current strong read chooses a safe read timestamp after 112. It then returns the newest versions at or before that read timestamp, A at 7,000 and B at 8,000, both committed at version timestamp 112. An explicitly stale read is different. The application deliberately requests an older safe snapshot, such as 90, usually to reduce coordination or latency. That request is valid when the application asks for it, but our earlier T2 did not. T2 requested the current strong state. Finally, version selection and replica routing are separate questions. A read-write transaction uses locks and the split leader. A strong read may run on another replica only when Spanner can serve the required safe timestamp there. Otherwise, it coordinates or waits. A stale read can remain local after that replica has replayed every log entry through the older timestamp requested. Now change just one thing, move B to split 2. The transfer and balances are identical, but A and B now have different leaders. If each split committed independently, the system could debit A and fail before crediting B. We need one decision across both splits. The client sends its commit request and buffered mutations to both split leaders and identifies the split one leader as the coordinator. The coordinator is one participant, not a third service. Both leaders acquire or verify the required locks. Split 1 locks A locally as coordinator. Split 2 validates B and holds its lock as the non-coordinator participant. Split 2 durably records prepared through its own Paxos group, then sends one yes vote to the split 1 coordinator. Prepared means my part is ready, my lock survives failure, and I will not finish until I learn the shared decision. The coordinator does not send itself a prepare vote. It combines its own successful lock with split 2's durable vote. A lock failure or any no forces abort only already permits commit. Now take the happy branch. The split 1 coordinator chooses commit timestamp 120 and uses split 1's Paxos group to durably record one commit decision together with A's mutation. In phase 2, the coordinator sends that commit timestamp to split 2. Split 2 replicates the commit decision through its own Paxos group before treating B as committed. The coordinator can apply A and split 2 can apply B at different physical moments. Each releases its lock after local application, and a required reader waits if the version it needs has not been applied yet. In parallel with that phase 2 work, the coordinator waits until TrueTime proves timestamp 120 is in the past. This is the same commit wait gate from the single split write. Only after the coordinator decision is durable and commit wait has passed does it return success to the client. Applying versions may overlap that reply, but any read that must include T1 waits for the needed apply. So, atomicity does not mean simultaneous physical writes. It means one durable decision, and no legal reader can observe A from one outcome and B from the other. Now, rewind to the alternate branch. If split 2 votes no, or the coordinator cannot secure its own lock, split 1 records abort. Both sides discard pending values, release locks, and keep A at 12,000 and B at 3,000. Now the harder failure, split 2, durably prepared, then crashed before learning the decision. After restart, its prepared record and lock remain. It must not guess commit or abort. Split 2 asks the split 1 coordinator group for the durable decision. The arrow runs from the recovering participant to the coordinator. The recovered answer is commit at timestamp 120. Split 2 durably records it, applies B at 8,000, and unlocks. Finally, test the 3 reader windows. A strong read beginning before the durable commit may return the complete old pair, or wait and return the complete new pair. A strong read beginning after the durable commit, but before client success must include T1 and may wait for one or both applies. A read beginning after success also returns only A at 7,000 and B at 8,000. No window permits one old account and one new account. Keep the responsibility separate. Paxos durably protects split 2's prepare, split 1's coordinator decision, and the replicated participant outcome. Two-phase commit turns those per split records into one commit or abort result, while TrueTime and commit wait protect the client visible order. What does this guarantee cost? Start with distance. A multi-region write waits for votes from a geographically distributed quorum. Signals cannot outrun physics, so placing voting replicas farther apart usually increases write latency. Availability also has a precise limit. If a majority of voting replicas is unavailable, the split may still have surviving copies, but it stops committing new writes. Stopping is safer than allowing two conflicting histories. Commit wait is not always a separate block of delay. Spanner overlaps it with replication, then waits only for any remaining TrueTime uncertainty. Schema design matters too. Spanner orders rows by primary key. It does not secretly hash them. A steadily increasing leading key, 901, 902, 903, keeps sending new writes to the rightmost key range. That overloaded range is a hotspot. One remedy is an application computed bucket before the account ID, such as hash of account ID modulo n. The hash spreads accounts statistically across several leading values. Account ID comes next, so one account's profile and order rows still stay near each other. That nearness is locality, and it makes related reads efficient. The bucket does not create permanent spanner splits. Split boundaries can still move. So when is spanner a good fit? When the system genuinely needs SQL transactions, horizontal scale, failure tolerance, and one strongly consistent source of truth across locations. A small regional application that accepts weaker consistency may be simpler and cheaper without all of this coordination. Let us rebuild the whole design from the problems it solves. Splits divide the ordered key space, and replicas keep copies in separate failure locations. Copies still need agreement, so each split uses Paxos and a voting quorum to maintain one ordered, durable log across failures. If T1 touches several splits, two-phase commit turns their separate Paxos-backed records into one atomic commit or a board decision. A single split transaction skips that cross-split protocol. Agreement alone does not preserve the order users observed. TrueTime supplies a bounded interval for timestamp selection, and commit wait hides success until that timestamp is safely in the past. The commit leaves timestamped row versions. MVCC later selects the newest eligible version of every row at one read timestamp, producing a consistent snapshot. Put those pieces together, and Spanner delivers externally consistent distributed transactions. The clock itself is not externally consistent. The complete transaction protocol is. That is the mental model behind Google Spanner. For more visual engineering breakdowns and role-specific learning paths, visit Cracking Walnut.